Hello, welcome to the hands-on. Before I go into the server, I would like to please, in the meantime, have your GitHub login ready. Look up your credentials. We're gonna need it in about 2 minutes. So before I go to the server, I first want to thank all the people who helped a lot with setting this up. Foremost, Steffen Bollmann. He really provided the server. He provided the entire infrastructure of making it possible that anybody independent of the operating system or installation environment can now participate just via the file browser, via Neurodesk Play, which we are going to use. And he spent a lot of time also testing it, making it usable for us, including the data and so on. I want to thank Gang Cheng, Paul Taylor, Farouk for specifically developing the code that we're going to use, but also working a lot with me to kind of prepare this simple little pipeline now. I want to thank Remy Gao, who kind of prepared and curated the dataset that we're going to use. It's the same dataset that was mentioned on Monday already. Specifically, it's a dataset from Luca Visioli with 2D multiband bold, and I will talk about this in a second too. So the goal here is to show you the specific logistical points through a layer fMRI complete analysis pipeline, where we go from raw data from the scanner to statistical profile difference estimations at the end. A lot of it is similar to regular fMRI, as we heard earlier today, namely we need to do motion correction alignment, we have a functional analysis, then we do kind of a segmentation of tissue types to find the borders of gray matter, white matter, CSF, to get that into layers, extract the signal, and do the statistical analysis. So now I want to talk about the specific logistical points of this part, which is unique to the layers. And the point is really to show you the tools that you can use. Maybe they're not the best tools, maybe it's not the most fluent experience here, but just to give you a first-hand experience on what's necessary and what goes into it. Then later in the second session, we will talk specifically about the functional analysis and how you can kind of push this and clean this a bit up. We will use the terminal for all kind of our analysis steps. So each of the pipeline steps that I showed you usually consists of a nifty 3D or 4D image that you push into an application command, and then you have a new output. And this is going to be used with this terminal interface. And then usually we have commands that start with ln for Laney, or 2D or 3D or 1D or PTA for AFNI, and you usually have the path to the file. And we will see this in action real quick. The dataset that we're going to use is this 0.8mm dataset acquired at CMRR. It's a multiband sequence. It's a very good dataset, I believe, fairly fast. It's the sequence parameters are fairly standard, I think, and it comes along with somewhat accurately co-aligned structural scan too. It is a functional data set, so we are particularly interested here in one of those visuals, cortex sulci. There are two task conditions that activate different areas positively, or the same area differently for the two task conditions. There are a few blocks. Each block is 12 seconds. We have the two different task conditions alternating in this case. And in fact, it's a person looking at a flickering checkerboard of the center and surround. So next, let's go to layer.neurodesk.org and start with all that. Okay, so I have my browser here, and I type in layer.neurodesk.org. And I'll wait a second for everybody to open their web browser and type that in. And I hit enter, and there we are. Now, this is why I wanted you to have your GitHub login ready. So I will sign in with GitHub. And my GitHub credentials would be, you will type in your own GitHub credentials now, please. All right, let's hope this works. Sign in. I forgot a Gmail here. Excuse me. Okay, now GitHub requires this two-factor authentication, so I will check my phone for the code, and I hope it arrives in a second, and there we are. And I will give Steffen Bollmann the authority to read my GitHub profile. And I don't need this. I will use the default environment and can start it. So I hope that everybody can follow along. Some people, some GitHub accounts are set up in a way that there's not an email sent to get the two-factor authentication code, and some of them require like the app. Usually it should be in about the time scale that I'm doing it right now, so I hope you can follow along. So this is now starting up the server, namely this NeuroDesk server from Steffen Bollmann. Okay, now we have here our Jupyter Lab, and there are multiple buttons, and the one that we want to use is the Neuro Desktop. This button right in the center here. So I'm clicking it, and now it's starting the Neuro Desktop. And we have different desktop available. We have a dynamic resolution or fixed resolution. Let's use any that you like. I'm using the dynamic resolution now. And here it asks me for permission to copy and paste the clipboard. And this would be valuable if you want to copy paste something from outside into the browser now. So I'm gonna allow this. So this is basically its own little desktop now. Make it full screen. And you have down here a number of programs. Specifically of interest is the NeuroDesk program. So it's a really cool environment. You can just run about anything in neuroimaging or fMRI analyses by selecting it here or looking at all the applications. There are quite a number of them. The first thing that we're going to do now is locate our data and put them to our desktop. So down here you have a little file browser to your home directory, and then within data we have our data. So specifically in data we have the data for the MGH layer course, and in the first hands-on now we're going to look at the layerification. So I'm going in here and basically dragging them onto my desktop. So I have them all here available. Please don't touch the data in that folder because we're going to all use the same copy here. So don't delete it, please. So now we have a bunch of data here. The nifty GZ are nifty data, and then we also have this file, which is a text file, which contains all the commands that we're going to run here. There are always kind of comments on how we execute them, and it's maybe about 8 commands that we're going to do in the next maybe 40 minutes or so. So I keep this open, maybe I keep it on this side here, and then first open a terminal to look at how we use the terminal. And based on the biosketches that I saw from people that registered, it looks like most of you should have some level of experience with using a terminal. So down here you see this black screen. Let's click on that. That's our terminal now. And we can type stuff in here, and I make it a bit bigger. You can do this too if you like or not. So I'm gonna first of all load the programs that we're gonna use. So the first command that we're gonna do is load the module of Laney. So module load Laney. We can copy paste this and put it here into the terminal, but you can also type it on your own. So now it's not complaining. So we all typed ML Laney, and it should not be capitalized at that point. Now we can see if it worked and just execute any Laney program. And I guess one of the simplest Laney program is ln_info. You can all type ln_info, and I hit enter now. And then you see this little kind of overall help menu that tells you how you can use it, what the options are. And you can always do this also with minus help. It gives you the same thing. So for example, here we can have input, and we can have certain kind of subsampling of the data. I'm going to turn this off real quick. So for example, let's look at our example data, namely the ANAT data. However, here our terminal, I think it is not on the desktop. So let's first move to the desktop where our data are. And you can move directories, probably you know this, with CD and then desktop. With the tab key, you autocomplete. So now I do CD desktop, and now we are in the desktop where all our data are. So now I can run lninfo on any of our Nifty files here. For example, I type in ln_info minus input, and let's look at the anatomical file, and let's subsample it with factor of 5. And maybe I make this full screen now, and let's see if this works. So first of all, it did not work because I didn't write input right. Input. So now it tells me some kind of metadata about my input file. It tells me which Laney version I have. It tells me what the resolution is, how many voxels I have, what the kind of the data type, how it's stored, and then what the orientation, the maximum, minimum, and so on is. If I continue with enter, it's not formatted correctly, so I will kill this and do it with minus inverse. Let's see if this works now. So here we have a little brain now that we can go through the different slices, and you can even see sulci or not. So it's basically a little ASCII art to look at your image. So now we kind of know that it worked, and we can go to the next command. Maybe I shouldn't have made it full screen. I'll make it a bit smaller now. Let's do the next command now and actually execute something that we are going to use for layer fMRI. So the first thing that we want to do is draw our RIM file, basically a segmentation in a viewer. So let's look at our anatomical image there, and we can open it, for example, in whatever ITK snap GUI. So basically I'm clicking on my anatomical file here, open with ITK snap GUI. So now it's basically loading that container that runs that command within Neurodesk. And whenever you run this program the first time, it checks you if it should update. I don't want it to update. It opened it, and now I can drag and drop the image into ITK snap as the main image here. So now I have my anatomical image. So basically, for those who didn't see it, I just drag and drop that image into my viewer. I have the 3 views. Actually, now I only care about the bottom view over there. And I click on the little C to make it a bit bigger. So now you can basically see we have our axial view here. We can zoom through a bit, and we have a nice cut-plane sulcus over here. So now with my right mouse key, I'm going up and down so I can zoom in. When I'm pressing and holding my wheel, I can move it up and down. The same controls are kind of available if you kind of zoom in with the magnification glass, or if you, as soon as you zoom in with the right mouse key going up and down, you can also kind of move around your center. So basically, this is the sulcus that we could care about. You can choose a different sulcus if you want. So what we want to with this sulcus is now segmented, and just for the sake of it, so we have a data set that we can use for later for the layerification. So I'm using the drawing tool right over there, which has a certain brush size and a certain label. It's drawing with the label 1. The brush size is 8, which is a bit much. So we want now, with the label 1, we want to draw the gray matter CSF borderline. So let's do that as thin as possible, namely with the brush size of 1. So basically I'm drawing somewhere at the borderline between gray matter and CSF, around this sulcus over there. And this is now approximately my borderline. With the right mouse button, you can kind of undo it, maybe because here I was too deep in CSF. It's always a matter of taste. I like to always not only have the borderline of gray matter in CSF, but actually a bit of padding on both sides. So that's why maybe I'm a bit more in CSF than some other people might think. It doesn't really change the result at the end. It just makes your layer fMRI profile a bit wider, padding it on both sides. So now that I have my gray matter CSF borderline, next I want to draw my gray matter white matter borderline. And for that I'm changing my active label here and going to label number 2. And it's a bit harder. Here it's clearer where we have our borderline. I think there it's relatively straight. Maybe I'm a bit too far into gray matter here, so I'm moving it a bit. So this should be approximately my gray matter white matter borderline. So now I have my borderlines, but I still need to kind of also segment my gray matter. So what I'm doing now is I increase my brush size a bit and draw with label 3. And I'm only drawing over labels that don't have a value in yet. So what I did here is I changed the active label to 3, and then I paint over a label that is clear. And I increase my brush size to 7 now. You can also do it differently. So basically I'm slowly drawing anything in between here that is not the borderline, but also kind of not on the other side. It looks like my 7 was a bit ambitious. It's almost too thick. And basically what I'm doing here is now filling this up, the space between CSF and white matter. So I have my chunk of cortex, and let's say I'm interested in my functional activation within this patch of the cortex. So let's save this, and you can save this by going to segmentation and save segmentation image. And the convention of how this is called is the RIM file. So I call it rim.nifty.gz, and I finish it. So now hopefully on my desktop I should have a RIM file, which is this one right over there. So I can use that now to calculate my layers. And the way how I'm calculating the layers is I'm using this Laney program LN2 layers. So let's look at what this program does. I'm copying this command and putting it back into my terminal. I'm going to the terminal that I opened before and not the one that execute my ITK snap. So here I'm copy pasting it with my right mouse key. So we learn about the program LN2 layers. You can scroll up a bit. So it basically tells you what it does. It generates layers based on the RIM file. It's usually, they like it to do on high spatial resolutions. And then there are usage commands. You can define how many layers you want. This is usually how, like example cases of how you might want to apply it. You need to tell it what the RIM file is. You need to tell it how many layers you want. For example, 3 would be the default if you don't say anything. You can include the borderline, which we just drew, and I would recommend to do that. And I think also specifically when you don't have very, very high resolution, it can be sometimes advantageous for fMRI application further down to use the equal counts. This basically separates then the cortical depth that you're estimating for each voxel, which is any value between 0 and 1, into bins of cortex, not based on the absolute distance metric, which can be equivolume or equidistant, but basically based on a percentile. So basically you chunk up all the voxels into equal sized patches of depth, which can help with some statistical things. You don't need to do this very often, but if you want to have similar histogram statistics or cortical depth, this is an option that we're going to use. If you want to find out more about those, there are these web links about blogs that explain the algorithm and more, which we are not going to look at now. So let's execute that with this simple command that I prepared. So this is now using the LN2 layers, paste. Using the RIM file that we just saved with 9 layers, and I'm using the equivolume approach with equal counts. which would be, I think, a good estimation for maybe 0.25 millimeter resolutions that we are working in here right now. This does not mean that the data were originally acquired at 0.5 millimeter resolution, but they were basically upsampled to that resolution, which does not mean that like the number of layers that you have are actually your ultimate true effective resolution, but it basically means that it allows you to have more smooth layers, and like in any histogram, it's a choice of your bin size. And usually I advise to use as many layers as possible, as we heard from Camille's talk already. So now this program is finished, and it wrote out a number of layers, layer files, metric files, the binned ones, the percentile chunked up file, and many more. The one that I care about now would be the rim layer bins equal wall, namely this one. Let's look at that. Let's go back to our viewer here. Maybe I can minimize the corresponding terminal here, and let's locate that file. Equibin, would it be that one? Equiwall, that's the one. So I load this as a segmentation image, for example. So now we see that this rim file that we generated has been converted into a layer file with layers that are defined based on equivolume, and we have 9 layers. So that seems to have worked correctly. So next thing is that we want to extract our functional contrast within each layer. And our functional contrasts are derived or provided in this case based on run average task conditions. So for example, if I load this as additional image, maybe we can see our functional contrast. Windowing is not the best, so now I'm using the S button to silence or make the segmentation disappear, and next I'm trying to adjust the windowing of this statistical image. So first I'm gonna display it as overlay, and then I'm adjusting the windowing of the image. So I went back here now to the crosshair mode. I'm selecting the file, click right, and go to the contrast inspector. And so here I think it would be maybe advised to go from, I don't know, 3 to 12. And we could use a color map that's somewhat looks like function, any that you like. So basically what I did is, in a contrast, I chose my minimum and maximum. Anything that's below the minimum is not visible, and the maximum is just where the ceiling is. So basically this is our functional contrast. Again, with the right mouse key, I can zoom in and out, and you can see that we have some activity here, not across the entire cortex or not with this thresholding, but we do have some activity. And now we want to see how that looks across cortical depth. And in order to do that, I'm going to look at a Laney program that's called LN2 profile. So if I use that, I copy it as a command in my terminal. Then again, it tells me all the options and how I can use the LN2 profile. And basically what LN2 profile does is look at all the individual voxels in a given layer, average them, and write them out in a text file. You can also plot it as ASCII art in your terminal if you want. And so basically what I'm doing now here is I'm taking this program, giving it all the commands that I think are helpful. Maybe I make it a bit bigger so you can see it in one line. So my input file is my function activation map. I give it my layer file, which is the layer bins that I just estimated. I wanted to plot it in the terminal, and I want to write it in this layer profile condition 1 file. If I hit return, it now estimates it across all the depth. It sees that we have 9 layers and then does a profile. So here what we see is we have a little layer from my profile as ASCII art, and you see it's negative. So with condition 1, there's actually a bold signal decrease, and the bold signal decrease is strongest in the superficial layers, not so strong in the deepest layers, close to white matter. So now let's do the same thing for the other task condition, the task condition 2. If I copy this and paste it in my terminal, I'm doing the same thing now for the other task condition for this individual image. And here you can see similar things. We have now a positive response. It's very positive at the surface and then kind of decreasing towards white matter. Maybe one feature that you might have seen already is that for the negative condition, the superficial layers, which actually is almost above the cortex, is actually strongest. So it's even here a bit concave. It's really dominated from the surface. This is usually not as bad for the positive condition, where kind of you have this kind of weaker slope. The most superficial layer is not really dominating it that much. It's still the strongest, but it's not as extreme. Okay, so let's look at maybe how this is, what the output looks like. We have our two files here. Maybe I open this with a text editor. So basically we have an ASCII, like a text file, where we have as a first column the layer number. The second column would be the percent signal change. The third column would be the standard deviation of all the voxels within that layer, and the third column would be the number of voxels within that layer. And per definition, we made the number of voxels the same because we divided it into 9 equal bins with the equal bins option. It cannot be perfect, so because like it's not divisible by 9 here, so 2 layers actually turn out to have 73 instead of 72 voxels. All right, for the other task condition, we can look at that too. So here we would expect positive numbers as the second column. Now, usually what we have here is we have these profiles for example, many different participants. And we have them for example, many different runs. And then we want to know, is one task condition statistically different than another task condition? And what we care about is not only knowing if they are different, but if they are different in a way that they're not just scaled versions from each other. Is the shape of the layer response different? And we cannot really compare them layer by layer, because we know that each layer is actually referring to signal across voxels that might have partial voluming. So as Farouk already mentioned in his lecture, the layers profile extraction is usually smooth. The effective resolution is not the number of layers. So we cannot really assume that they are statistically independent, these different data points. Similarly, we don't really know what the effective resolution is. So we need a statistical way to estimate that estimates the smoothness based on the data. And we also don't really care much if the values are different, but are just scaled versions from each other. We care about the shape of the layer from our profile and want to know if that is different. And this is all done based on in PTA, which I can show you in a second. Excuse me. So this is an AFNI program that's developed by Gang Chen, and it's published in this paper, basically assuming that different points are smooth and then using this smoothness and seeing how the shape is different across cortical depth. And this is what we're going to apply now. And we're going to do this with the specific file program that is called PTA, and that's part of AFNI. So now I close my conditions and I first load AFNI with module load AFNI. And I think it would be helpful to use this very specific version of AFNI, because here in sometimes the Unicode characters of different R modes installed here might not work. So let's use module load AFNI, and let's use the 21.2.00 version, which is another beauty of NeuroDesk, that you can basically just choose the version. So now let's execute that. This PTA, I copy this and put it into my terminal. Let's look at the entire command here. So what we give it, it's PTA stands for profile tracking analysis. The output would be the D1. The input would be a table that contains all the layer profiles that we estimated. And I can show you how this looks here in this table. So basically we have the run which starts with S, for example, in the first run, and the condition -1, we have this value in layer 1. In the first run in layer 2, we have this value for the condition -1. And then basically in this format, you can see that for all the different runs and all the different conditions, you have basically a big text file, which is then read in this form by PTA. We look at the model. Basically, we're looking at the layer effect, and we have the runs as a random effect, which is the model. Then we spit out the prediction as the P1. So if I execute that, it takes a second. It goes through all the runs that we have, looks at the layer profiles, and now it was successfully performed, and we have two outputs, namely the prediction and the stat. Here the prediction, here the stat. Let's look at the stat first. Here this would be our stat file. Let's open it. So here we have all kind of statistical values. In our case, we have a very strong positive bold response and a very strong negative bold response. So the magnitude is hugely statistically different. F value is gigantic and P value is tiny. What interests me more though is the effect of the condition on the shape. So here the second value would be the shape. So we learn that here the shape would be significantly different. And we can actually then also look at the prediction from the PTA and see where the shape is different. And the prediction here would be this text file, where we basically for each run, all run have the same prediction because we assume that they are same, but for each condition, the plus and -1 across all the layers, we have a given prediction and a standard error of that. And if you don't like looking at data in this form but actually want to plot it, we can also do so by using a very simple 1D plot. It's an AFNI thing where you can plot it and look at it in the terminal. If we execute that, you can see here that we have a positive response and a negative response. And you can see that the positive response is like above 0. The 0 line would be there, and the peak is somewhere over there. It's close to the surface, but it's not really the surface. And in this case, white matter is on the left and CSF would be on the right. Whereas for the negative condition, we have this slight shift towards the surface. So there's something going on here. With respect to the task modulation, they're not just scaled versions from each other, which is good news. We have a task effect here, and it's statistically significant here across runs. All right, this concludes the first part of this hands-on. And after the break, we will then also look at statistical analysis of activation maps and how we clean them up.